Okay, so thanks. First, thank the organizers for inviting me and putting up this wonderful conference. So I'll be talking about a Fracton topological phase, and I think I'm the only one who touches on this topic. So I'll spend some time to give introduction to what are Fracton topological phases and why they're interesting. Okay, so get started. So of course we are all interested in gapped quantum phases, as you have probably heard from yesterday's talk, that we are thinking about a many-body system, quantum many-body system on a lattice with local interactions, and we assume that system has let's assume that system has a gap in thermodynamic limit. Okay. Now, for such systems, there's a well-defined notion of quantum phases given by adiabatic continuity between the ground states of different Hamiltonians. Here I just show a two-dimensional plot in a parameter space of 4 Hamiltonians, and if these two Hamiltonians can be adiabatically connected to each other by smoothly varying the parameters, and the ground state of h of 0 is transformed to ground state of h of 1, then we say that these two ground states are in the same quantum phase. And different regions, different colored regions, are different phases separated by phase transitions. But the important further distinction was first pointed out by Xiaogang and Beizhen. That is, we further need to distinguish quantum phases that are liquid-like and non-liquid-like. And the question arises because we have to take sequences of systems of finite volume to approach thermodynamic limit. Okay. And for gapped quantum liquid, what it means is that, well, for a gapped system or a topological order system of a certain size, we can grow it, we can make it larger by just bringing additional trivial states, and then put these two things together, and then doing some local unitary transformation or just adiabatically evolve the composite system until we get to a larger system size, until the system size becomes, until the system becomes a topological order state on a larger size. Okay. And if this is possible, then we say this is a gapped quantum liquid. Okay. So gapped quantum liquid captures part of the, some of the features we expect from a system that can be described by quantum field theory. Okay. So it's natural to kind of conjecture that gapped quantum liquids are actually described by topological quantum field theories at low energy. But the definitions, of course, meaningful only because there are non-liquid states. And a simple example, but an extremely boring one, is just a stack of two-dimensional topological order phases in 3 dimensions. Okay, I'm not aware of any non-liquid states in lower dimensions, but in 3D, because of the existence of two-dimensional topological order states, you can just stack them up, and you'll get a 3-dimensional gapped phase. But this is not a liquid because if you want to grow the size of system, say you have to add additional layers, but these layers cannot be just generated from adding trivial states. You have to add these 2-dimensional layers, which are long-range entangled. Now, this makes it a non-liquid state. And you can also see that different number of layers correspond to different number of topological ground states degeneracy, so they cannot be adiabatically connected to each other for systems with different number of layers. So we have a nice classification of bosonic quantum liquids, well, also fermionic, I guess, but here I only give the bosonic ones. So we know that in 1 + 1, there are just all trivial states. Here there are no symmetries. And in 2 + 1, it is, well, at least believed and with very strong evidence that all the topological order states are described by a unitary modular tensor category. And in 3+1, the recent work of Kong, Tianlan, Xiaogang, Zheng, and Johnson, Seal, Johnson, Freight have provided provided strong evidence that everything is topological gauge theory. Okay. So all these are very nice, but there are these in recent years, a new class of models have been discovered. They're all in 3+1 that just simply do not fit into this framework of topological quantum liquids, but this class of topological quantum liquids. And in some sense, they are much more interesting non-liquid states. So the first example was actually discovered very long ago in 2005 by Claudia Schaumont. It was known as Schaumont's model and was just forgotten for almost 10 years. And it was under the name of quantum glassness. Okay. And after 6 years, there was another model that came up by Joan Haah in the context of quantum information theory as a self-correcting quantum memory in 3+1. That is a lattice model that I will describe briefly. And he actually put up 18 models of this kind. And this is the most famous one, the first one out of 18. So we don't really have a mathematically rigorous definition of Fracton phase yet. Well, not even quasi-rigorous definition. We don't have such a definition right now. So I can only describe some kind of phenomenology of a Fracton phase that are commonly accepted as common features of Fracton phases. So these are still gapped quantum phases, typically defined on a lattice Hamiltonian, and you get topological degeneracy on torus just as all the Fermian topological phases in lower dimensions, or TQFTs. But the degeneracy typically grows with linear size of system exponentially, meaning that if you take a log of the ground state degeneracy, this log asymptotically grows with this linear size of system. It may not be exactly a linear function, but there are asymptotically, this is the way that the degeneracy grows. And all these degeneracies, all these degenerate states are topological in the sense that they cannot be distinguished by local measurements. So they're as topological as all the other topological ordered states that we know and love. Okay. And related to the exponentially growing number of degenerate ground states, the quasi-particles are also somewhat unusual that they have restricted mobility. Meaning that if you, in the generic Hamiltonian, you typically expect that the quasi-particles can move, and although they're gapped, once they are excited, they can move around and give you some dispersion relation. But in these Fracton models, the quasi-particles, even under very generic perturbations, they do not move, or they can only move in certain directions. So the stack of two-dimensional topological order states is a toy and a boring example of Fracton phase. It satisfies all the three has all the three features that I mentioned. It has topological degeneracy on 3 torus that grows exponentially with the number of layers, and the quasi-particles are anyons in the 2D layers, so it can only move in the two-dimensional planes. Cannot really move in the third direction. Okay. But there are much more interesting examples as I show here. So let me describe one such model with more details. And this is kind of the prototypical model for a large class of Fracton phases. And first, due to its simplicity, it's much simpler than the two models that I mentioned earlier. So it's called X-cube model. And the model can be easily written down on a cubic lattice. Okay. So let's consider a cubic lattice where we have qubits on each edge. This is a bit like the usual Z2 Tauri code in 3 dimensions. We have qubits on each edge, and the Hamiltonian terms are drawn here. So the first term is just the product of all the Pauli X operators on the qubits on each edge for one cube. So you just multiply the 12x Pauli X operators, and that's and sum over all such products. And this is the first term of the Hamiltonian. And the second term is a product of the 4 z's out of one vertex, out of one site. And there are 3 ways to choose these 4 z's. Well, the 3 planes, xy, yz, and xy, yz, and xz. So you just multiply these 4 z's and then sum these terms up. Okay, it was first written down by Sagar Vijay and Zhou Wenhao and Liang Fu some 4 years ago. So it's a simple model. I mean, simple in the sense that it's not that complicated compared to the usual C2 code in 3 dimensions. However, the excitations are very different. So here's a kind of illustration of the kind of excitations that we can get from this model. So because of these terms are just products of Pauli operators. This is product of Pauli X, and these are product Pauli Z, and each of them square to 1 just because Pauli operators square to 1, and they all commute with each other. So the ground states just simply minimize all the terms simultaneously and set the values to 1. So if you choose the coefficients to be negative, and excitations are generated by flipping one or several of these terms to -1. Okay. So there are obviously 2 kinds of excitations. One is flipping some of these cubes to -1, and these excitations, as if you play around these models a little bit, you see that you cannot generate just a pair of these cube violations. You have to generate at least 4 of them at once, and the operators that generate these 4 are actually supported on a sheet, on a square sheet like this. And I emphasize that this is really a square sheet. It's not like a fluctuating membrane. It's really a rigid sheet like this. It doesn't have to be a square. It could be a rectangular sheet, but it has to be a sheet like this. And you get these violations at the 4 corners of this square sheet. Okay, and you can only move them by just making the sheet larger. So you can maybe you can move the 4 of them together, or move these 2 together just by growing the sheet in some direction. Okay. So this already suggests that this model is very different from the usual kind of topological order states we're familiar with, because there are no string operators that create and move these excitations. You can only generate them on the corners of the sheet operator. Okay. So if you have one of them isolated somewhere and the other 3 are moved far away, you cannot really do anything to this guy by local operations. So they're just stuck there. It will just stuck there. Okay. Now, the other kind of excitations are the violations of these Z terms. And it turns out that now you can create a pair of them, okay, by a string operator along this line, along this blue line. However, you can only do this along this line. You cannot make a turn. You cannot turn it around. When you turn it around, when you turn it to a different direction, you have to generate additional excitations. So there are no cost-free ways to extend this string operator in a different direction. It just goes in one direction. Of course, they can go in a different direction, but once you choose a direction, depending on which two of these which 2 of these terms you want to excite, that determines which direction you can go, and that's rigid. Okay. So there are these completely immobile cube excitations, and they are called fractons, and then there are these excitations that can move along a line, and they are called linons. Just names that we cook up to describe these particles with restricted mobility. Okay. And we can also compute the ground state degeneracy on a torus, just by imposing periodic boundary conditions on the cubic lattice. And this is a stabilizer model, so it's easy to count the number of ground states. And the result we get is 2 to the 2Lx plus 2Ly plus 2Lz minus 6. So there's this exponentially growing piece, but then there's also a constant offset. Okay, and all these ground states are topologically protected. They cannot be, they are not coming from some local stuff. It's really topological. They're all topological ground states. And I just mentioned that because of this Z2, because these Pauli operators, so all excitations have kind of Z2 fusion. So they only take value plus minus 1 for these terms. Okay, and I'll just show one more example just to get some idea of how bizarre these models can behave. So this is another model, and it's again written down on the cubic lattice, but this time we have 2 qubits per site, not on the edge. On each qubits are defined on each site, and there are 2 qubits per site. And again, these z's and x are Pauli x and z operators. The I is an identity operator. So the Hamiltonians are just sum of these 2 terms, okay? 2 cubic terms. Okay. And again, you cannot create just a pair of excitations. You have to create them following a particular pattern. This pattern is like a tetrahedron. You can create excitations on the corners of a huge, not just tetrahedron, it's actually a kind of fractal shape in 3 dimensions. You can create excitations. The minimal one is a tetrahedron, but you can now imagine stacking them up to grow it larger and larger, and you get 4 excitations on the corners of a kind of huge 3-dimensional Sierpinski, three-dimensional version of Sierpinski bracket in some sense. And the bottom line is that there are no string operators of any kind in this model. So all excitations are immobile, completely immobile. And you can also count the number of ground states, say L by L by L torus. And here, the figure just shows a log, the base 2 log of the ground state degeneracy. And you can see that it has an envelope that is roughly growing linearly. Okay, this is from L to 100, this is from L to 1000. You can see that roughly there's an envelope that grows linearly, but it fluctuates wildly, extremely wildly across different size of system. Even you change the system size by 1, L goes to L plus 1, the ground state can change by a lot. Okay. So all these features are quite bizarre, and it's obviously not a topological quantum field theory of any kind. Right? The topological quantum field theory does not care about the size of the system, at least not to this extent. And obviously, all these models have a very strong dependence on the underlying lattice, at least naively, and they somehow remember lots of details of the lattice structure, at least the size of the system, for example. Okay, so you might wonder that I just give you 2 very special isolated examples, but turns out that there is now a huge list of models that are fractonic in one way or another. So I've mentioned that there are 18 qubit codes from Joe Haah's work, and then a bit later, Ben Yoshida wrote down an infinite family of similar kinds of models. He called it fractal spin liquids, and XQ model and similar models, checkerboard, Chamon, and then there are a few very general constructions that I'll briefly touch upon. Okay, so many of them, all these models are kind of commuting projector models, exactly solvable, so you can go and study their properties basically as much as you like. So if you want to see kind of a summary of the phenomenologies of these stabilizer models, you can check out this paper. Okay, so here, let me just introduce a few terminologies. So I've already started using them. So if a particle is completely immobile, it cannot go anywhere. It's called a fracton. I mean, it's probably should be called a pointon. A fracton might remind you of fractals, although not every one of these models has anything to do with fractals. And then if the particles can go in some direction, but only in that direction, then we call it a linon. And if a particle can go in a plane, then it's a planon. So it's just fairly obvious ways to kind of name the mobility. And of course, there are just completely immobile particles. We just say they're mobile particles. And there's some kind of typology, but I don't think it's important for my purpose. So I wonder, though, we have all these exotic models. They're just like beasts. They're very weird. How do we understand them? Whether are they related to the TQFT that we are familiar with in any ways? Or so how can we kind of fit them in some kind of nice framework? Well, up to now, we still don't have such a framework. We don't really have a systematic mathematical theory to describe these fracton phases. But there are ideas that there are recent ideas that can sort of at least encompass a large class of fracton models by connecting them to TQFTs. That's something that we like to see, connecting to TQFTs. And the basic insight is that one can build a three-dimensional fracton model from stacks of, say, lower dimensional TQFTs, like the two-dimensional topological order states, and possibly embedded in the three-dimensional TQFT. Okay, just imagine you have a three-dimensional space, maybe already with the topological quantum field theory in it already, like a toric code, or some other topological quantum field theory that you can choose. And then you embed these two-dimensional layers or defects in the three-dimensional topological quantum field theory. And then, of course, if you just embed them and do nothing, then it's a boring kind of stacks of TQFTs. But once you couple them, when they intersect, these layers intersect, you can couple them in some way, and then you start getting interesting models. And this is and these couplings kind of determine the mobility of excitations. Okay. So I'll just show one example of such a kind of stacking construction, such a network construction. So suppose each of these layers is a two-dimensional Z2 toric code, just the mundane Z2 toric code that we are familiar with. And we know that Z2 toric code has four kinds of anyons: one, the vacuum, E, M, and then bound state psi. Okay. Now, suppose you have two such Z2 toric codes intersecting each other, and we want to figure out what happens at the intersection line, right? So to see what happens, let's kind of cut these two layers into four pieces, and they are joined together at this line. Okay, so we first cut them and then glue them together, choosing appropriate boundary condition. So if you kind of unfold this four layers, we need to kind of choose a gap boundary condition for these four layers of toric code. We can just choose a kind of a simple boundary condition that corresponds to a simple intersection of these two layers without really doing anything. So a particle from here can just go to the other side, or a particle from the top part can just go to the bottom without doing anything else, and that gives you a trivial intersecting layers. And here, this way, we just get boring stacks of two-dimensional toric codes. But we can do things a bit differently. So, for example, we can still allow the E particles to just kind of pass through this boundary, without encountering any other effects. But when the M particle tries to go through the boundary, okay, it has to emit an E particle to either this side or this side, doesn't really matter. Which means that we condense these three particles at this junction, at this intersection line. And similarly, we condense these three particles, M, and E. And you have to condense more just by combining these kind of generating anyons in the condensation. But this way, you can convince yourself either through an explicit lattice model construction, or just by thinking about what happens when you bring in an anyon at this intersection, and what happens when it tries to go further, that this actually gives you the X-cube model. Okay, so when you do it at all intersections, you get the X-cube model. So quite recently, actually earlier this year, a few groups have put up this kind of a very general construction as a kind of defect network. This is a name in this paper by Asen, Baumesh, Slagle, and Williamson, and Xiaogang Wen also, and Zhuwen Wang studied a similar kind of construction under the name of a cellular states, again, because of this kind of construction, that is, you first split the space into cells and then put topological order states on each possible cells and then glue them in some appropriate ways. Okay, it seems a very general construction, and that covers a large class of models, Fracton models we know. Okay, so we may wonder whether this is the complete story, whether all the three-dimensional gap faces are either TQFTs, of course, or they're just TQFTs plus additional defects layers and embedded in the TQFT and coupled in some way. Okay, choosing appropriate boundary conditions, etc. So again, this is an open question. We don't know the answer, but I want to describe some, from now I want to describe some models that have features which seems hard to fit into this kind of construction. Of course, we don't know for sure, but I'll explain them and then in the following. So let's go back to this toy example of stacks of two-dimensional toric codes. Okay. And we know that, as I said, this is a boring example of Fracton phase. We just have a stacks of 2D toric codes and nothing else, of 2D topological order phases and nothing else. So maybe we can, but all the particles are anyons in the two-dimensional plane, so they are just planons trivially. So it's a topological phase, it's a Fracton phase with only planons. So maybe we can ask whether there are more interesting phases or models that have only planons. So for example, what you can do is maybe you can start from a stack of two-dimensional topological order phases and do some kind of anyon condensation between different layers, across different layers, like what I showed here. This is Z4 toric code, and they'll condense E square and M square across neighboring layers. Okay, you can get some interesting planon phases. But I don't want to discuss this particular model. I want to discuss a more general family of models that we call infinite component Chern-Simons theory. Okay. So the model goes like the following. So again, we have kind of virtually some layers. I mean, they're not really layers. They're not physically separated layers, but we have gauge fields. We have U1 gauge fields living in these different layers, indexed by the layers. Okay. And suppose that we start from some kind of Laughlin layers, meaning that each layer is described by a Chern-Simons theory, U1 Chern-Simons theory at level M. And now we want to couple the layers, but we want to couple the layers by mutual Chern-Simons terms. So here's the Lagrangian of this three-dimensional layer system. So the first term is just the level M Chern-Simons term for each of the layer, for the gauge fields in the ice layer, for example. And then for neighboring layers, we have Chern-Simons terms, mutual Chern-Simons terms of level n. Okay. So we can write it in a kind of a K-matrix formalism. So Lagrangian is now written as AI dAj, and the wedge product. And then these coefficients are packed into a symmetric integer matrix, which I called K, and it looks like this. So, well, I think I had a wrong entry here. So the diagonals are just the same m, coming from the first term, and off diagonals only appear next to the diagonal lines. You only have these off diagonal elements, and these are the neighboring the mutual Chern-Simons term for the neighboring layers. So this is an infinite component Chern-Simons theory with U1 gauge fields at each layer. So you have an infinite number of U1. You have an infinitely large U1 gauge symmetry, U1 infinite gauge symmetry. Okay. And no, this is certainly something that's very natural to write down as a three-dimensional field theory, at least. Okay. But if we try to study this infinite component Chern-Simons theory, we see that there are a number of somewhat strange characters. Okay. So first of all, this K matrix is local in the layer index. We only couple gauge fields, either from the same layer or from neighboring layers. So it looks like it's a kind of local quantum field theory. But if we try to do a canonical quantization of this theory, just quantize it, just following the usual recipe for quantizing a U1 multiple component U1 Chern-Simons theory, we'll see that these gauge fields, this is just a general result for K matrix, that gauge fields have to satisfy this kind of canonical commutation relation, the AX component of A of I, the I's layer, and the Y component of the J's gauge field. They don't commute, and they have the commutators given by the inverse K matrix, the IJ's component of the inverse K matrix. Okay, and of course with the delta function. So if you look at this K inverse, so the K was given in the previous slide. Oops, I think I'm jumping ahead. The K is given in the previous slide, but now if you just calculate K inverse, you find that the K inverse has matrix elements spreading over all the matrix elements, all the entries. So for example, when m is greater than 2 times n, you get a K inverse decaying as a exponential, as a separation I minus j. And if in the other case, K inverse, the matrix entries oscillate with I minus j, but they never go to 0. So in a sense, K inverse is quite non-local. You have K inverse spreading all over the whole matrix. Okay. So it seems like these fields, they do not commute even when they are very far separated. So even we think these fields come from layers that are separated very far, but they still don't commute. So you might wonder, whether this is actually compatible with a kind of a local Hilbert space, okay, because naively, it requires fields to kind of have commutations even when they are very far apart. And of course, this can be directly translated into a kind of a topological effect, meaning that anyons that we thought were localized in some layer actually have braidings with anyons localized in layers that are very far apart. Okay, so before I go further, I want to just mention that the generic features of these models, to understand the generic feature of this model, we have to add Maxwell terms. And once we add Maxwell terms, we see that then we can calculate the photon spectrum. And when it's only gapped when m is greater than 2n. If in the other case, it's actually the photons are actually gapless. So I'll focus on the gap case, and I don't have anything to say about the gapless cases. Okay, so we can just take this field theory and study their topological order. So as I mentioned, all the anyons are planons because all these U1 gauge fields are kind of two-dimensional U1 gauge fields, 2+1 U1 gauge fields. So no, it's natural that these anyons are still planons, but you can check that they are typically infinite order fusion, unlike any finite under other finite rank Chern-Simons theory. They have finite order fusion, but here the fusion rules are typically infinite order. You can calculate statistics between anyons and also ground state degeneracy, which grows exponentially. I mean, with some correction that I ignore, I only keep the leading terms in the expression, but this base of this exponential growth is actually an irrational number in general. Okay. Of course, this is the result of a thermodynamic limit, and there are other corrections to make it integer, but the asymptotic growth is controlled by this term. And we can also look at the surface of this Chern-Simons, of this infinite component Chern-Simons theory. You see that it's a kind of a highly anisotropic two-dimensional chiral Luttinger liquid, or not necessarily chiral, but in this case it's chiral, chiral Luttinger liquid defined by this K matrix. Okay, so this is somewhat strange because of all these unusual features. No, but again, there was a problem that we didn't resolve so far. That is whether this model can actually arise from a local theory because of this unusual commutation relation between fields. So there are a number of physical realizations. So we can actually, for certain m and n, when they're both positive, we can actually write down a fraction quantum Hall wave function to realize this infinite component Chern-Simons theory. And this were actually studied in the 90s in multi-layer quantum Hall systems. I can also write down a more explicit lattice models starting from a stack of integer quantum Hall states and then gauge certain U1 symmetries that only couple to some of these integer quantum Hall layers in the right way. Okay, but I want to discuss a slightly different construction that goes under the name of coupled wires, okay, where things are more explicit. So these coupled wire models are a kind of class of Hamiltonian models that we use to study topological phases in both 2-dimensional and 3 dimensions. And the building blocks of these models are one-dimensional quantum wires. And each of them is a free compact boson. In the simplest case, we can have other component field series in these wires, but the simplest choice is just a free compact boson, which is arguably just the simplest quantum field theory one can think of in 1+1. And just a free bosons, so they're without any interaction, they're just a free theory. And depending on whether you have fermions or bosons, you may have this chiral left-moving or right-moving fields. That's kind of natural for spinless fermions, phi1 and phi2, the left-moving and right-moving fields. And then if a bosonic wire, it's usually more convenient to write it in terms of non-chiral fields, phi and theta, which are conjugate variables. Okay. So the starting point is just these coupled wires and array, well, just these wires so far not coupled and positioned in a 2-dimensional array. So you get a 3-dimensional system. Now, of course, we want to couple them in some way to get to lift this degeneracy. So far, it's extensively gapless, but now we want to couple them using interactions to lift the degeneracy and maybe get a gapped phase. So the first example that I want to discuss is a coupled wire model for this infinite component Chern-Simons theory. Okay, so the kind of interaction is schematically shown here, and I mean, I don't think one needs to read into all the details. And the point is that what this shows is just fields on different sites, and this is a small cluster that are coupled together. And we add all these fields up. These are bosons. These are free bosons in 1D. So these are just angular, well, these are just phases or angular variables. We can add them, and it's compact. So interactions have to come in this kind of cosine. Okay, so these are just cosine of the sum of all these fields in this small cluster. Okay,
And then we just sum over all such terms, translate it to different parts of lattice, and then turn on this interaction. Okay. And let's assume that interaction strength is large enough, so these terms open a gap in the spectrum. And again, we can show that just by analyzing the Gaussian limit of this model, that when the m is 2 times larger than 2n, the bulk is fully gapped. And roughly speaking, you'll get what we want is an infinite component Chern-Simons theory with this K matrix on this side, but the top is gapped. That's quite natural from the picture that I described earlier. Okay. Now the excitations in these couple wire models come in 2 types. So the ground state has all these fields pinned to 0, but you can have these fields kind of oscillate around the minimum defined by these cosine terms. There are small oscillations around the minimum. These are just phonon excitations. They're like the phonon excitations in the lattice. And these are gapped when this condition is satisfied in this model. Now, there are other excitations that kind of tunnels from one minimum to another, which means the value of this capital theta kind of winds from 0 to 2 pi in a very short distance along the wire. Okay. So these are small oscillations, but this is a kind of a big oscillation, big shift of the fields that happens in a very short distance, so you get kind of a soliton-like excitation. And these soliton excitations are gapped. The gap is given roughly by the velocity of these boson fields times the interaction strength u. And there's a strength that tells you, how many values you have jumped over. So if you tunnel from 0 to 2 pi times k, this is kind of strength k excitation. Okay. So in this case, in this model, one can explicitly write down all the kind of operators, string operators that can be used to move these particles around in these 2-dimensional layers. You cannot move it across the layers, across the z direction. So I didn't mention that the directions, but this is y and z, and then the wires going into the board. That's the x direction. So suppose this is excitation. This is a soliton excitation for one of these thetas, and then we can move it in this direction with a series of e to the I theta terms. And we cannot move it across along the z direction. And we can move it around the x direction, but you have to use a much more complicated operator. So I don't want to explain the detail of this operator, but just to mention that this operator involves all the fields along this column. So basically, for all the sites that are inside these 2 red lines, you have to involve all these sites. Although once you go away from the location of excitation, the weight of these sites, the weight of the operator on these sites away from the point decays exponentially. So in a sense, it's still kind of a localized operator, but it's exponentially supported even when you move away from this excitation. And that's why in the low edge limit, you have these fields have non-trivial commutation relation even when they are far away, coming from that come from these exponential tails, even though the model itself is completely local. Okay, so this is a microscopic model of this infinite component Chern-Simons theory, and we see that this somewhat unusual commutation relation really is due to this kind of a very exponentially localized string operators, which is nothing. There's nothing wrong with such exponentially localized string operators, but here it gives you somewhat unusual braidings in a 3-dimensional system. So there are many models you can build in just starting from a couple wire. So I want to briefly mention another model. This time you have 2 wires, you have 2 number of wires on each side, and then we couple the 4 wires around 1 plaquette. Okay, so the details probably don't matter. The couplings are defined on each plaquette. Again, there's a Hamiltonian one can write down, And this time it's convenient to use a kind of a fermionic wire. So you have left moving and right moving fields. But then there's a condition, though there are some parameters one can choose to define this model. And when certain conditions satisfied, it's fully gapped. Okay. And again, excitations are solitons of these cosine terms. Now it's kind of defined on each plaquette. And it's it has a strength k that tells you the soliton winds from 0 to 2 pi times k. And any strength k soliton in a single plaquette is a non-trivial excitation, meaning that it's kind of an infinite fusion. Unlike the usual kind of anyon excitations, they don't have finite order. It's an infinite order excitation. And in general, these particles can only move in the y direction, meaning that the y direction going into the board. And in the plane, what you can do is that you can isolate one such excitation with the price of generating a huge excitation, exponentially large, with the distance you want to separate them, somewhere far away. If you want to separate these two, the other side has to be exponentially large, meaning that you actually have to pay a large energy on the other side. But you can isolate one such excitation. Okay. So it's not too surprising that these coupled wire models produce line-on phase, because after all, along the y direction, we have a quantum field theory, a free boson CFT to start with. So things are kind of nice and continuous along the wires, but in the other direction, because of the lattice and the particular way that these wires are coupled, we get a kind of fractonic-like model. I will wrap up pretty soon, but I just want to mention one unusual feature of this model. So as I said earlier about this infinite component Chern-Simons theory, they have gapless chiral Luttinger liquid, kind of a 2D version of Luttinger liquid on one of the surface, and the other surface is gapped. So it's already like different surfaces have different theories, but that's not too surprising, since we already have that as a stack of two-dimensional topological phases. In this model that I just defined, again you'll find that you have an infinite component Luttinger liquid on different surfaces. For example, on the XZ surface, you get this K matrix. You can calculate what these entries are. But if you take a different surface, say the YZ plane, one finds a very different, I'm not even sure the labeling is correct, but no, the bottom surface here, you find a very different K matrix. Well, it's similar looking, but the entries are actually different, although it still looks similar. But you can cut through the three-dimensional system again in a different direction, and exposing a surface of a different orientation. This is kind of 1, 1, -1, well, the -1, 1 surface. And now the K matrix look again very different from the previous two. So every time you cut into the system in a different direction, you get a different Luttinger liquid. You get a different chiral Luttinger liquid with very different properties. So so this just kind of suggests that at least it's difficult to think of this model as coming from some kind of underlying two-dimensional stacks, because every time you cut into the system, you see a different infinite component K matrix, and there's no preferred choice of any direction. Okay, so just summarize. So just maybe the take-home message is that for this audience, that there are a rich variety of non-liquid gap phases in 3 dimensions, and most of them occur in these Fracton models, and many of them can be obtained from this 3D TQFT plus the stacks of 2D layers or defects. But I also discussed these other Planon and Line-on models with somewhat unusual properties that are unexpected if you have this picture. Okay. So I'll just thank my collaborators in these works. Dominic Williamson now have
moved to Stanford, and Arpit and Joe, they are graduate students at Yale. Arpit will start in Caltech soon. And then these collaborators from Caltech, Xie Chen's group, John McGreevy, and Michael Levy. So thanks for your attention.
Thank you. Let's thank speaker. Maybe we have only time for maybe 1 minute. Well, sorry, one questions for single questions before we take a break. Oh yeah, Nathan, Cyber Guanan.
So you described models constructed out of planes and models constructed out of wires. So
right.
The next thing would be models constructed out of points, and it's the same as doing nothing, because every system is really a system made of points. So what's the benefit of the lines and the planes in the construction? Because you can always embed them in models of points, right? And the models of points are everything.
Yeah, of course. So it's not like, of course, you're absolutely right that in the end of the day, of course, we start from just local tensor product of local Hilbert spaces. But I think one reason to think about these, starting from some planes and starting from some wires, is that we already know what happens at least in this lower dimensional system, right? So we can write down a nice field theory in the two-dimensional plane, can have this nice field theory in these one-dimensional wires, and we know how to manipulate these field theories. And then we build up the three-dimensional model by coupling these field theories. So we have some kind of grounds to begin with. This is kind of same thought or same benefits from, say, you start from a stack of these layers and try to couple them. But here, I think the difference is that we couple them in the very different ways. And the wires, of course, the wires actually for the wire model. I think it's even more flexible than coupling these two-dimensional planes, because we don't assume any two-dimensional quantum field theories to begin with. And as I argued, this may not be true, but it doesn't seem like there's any two-dimensional field theories embedded in these wire models in the last example I discussed. But again, this is just a construction that I find convenient, and it's also analytically tractable in many ways.
So I also have another question.
Yeah.
If I may. It's a two questions. One is, once the layers are coupled, then in what sense are they really layers? Is there a clear separation between a system of coupled layers and a system with no layers at all? Because every system can be thought of as a system of layers with some coupling between the layers.
Yeah, so that might be a confusing name. So I think it's it's just really to name this construction. There's indeed, once these layers are coupled, especially coupled in this way that in this, say, the mutual Chern-Simons term that I discussed, they're really not the separate layers anymore, although there's still a sense that, say, these gauge fields are defining a certain layer. At least we attach a layer index to them. And we imagine that these gauge fields are somewhat localized to layer, although from the computation relations, you can see that they're not really localized to any layers.
But you have the same thing in any field theory. If you have a field theory in X, Y, and Z, then you can think of these are layers in the XY plane, and Z is a label.
Yeah, that's right.
These are layers labeled by Z.
Yeah,
so
I absolutely agree.
Is it different than a non-layer model?
Yeah, I absolutely agree. Yeah, from the point of view of construction, there's, once you couple them, then the layer index may not be, just the index of the three-dimensional space. There's no significant meaning to them. But in this particular case, at least in the final result, the particles, excitations, they are indeed localized in these different layers, and they can move in each of these planes, stuck in these planes. So in that case, in that sense, there's still a kind of meaningful notion of different layers.
If I can ask one final question, in the model with the K matrix, is there any sense in which the model has a three-dimensional spatial symmetry, or at least cubic symmetry? Because it clearly has symmetry in the rotation of the plane of the Chern-Simons theory, but the other direction is treated different.
Yeah, so these models are, both the plane model and line models are very anisotropic, highly anisotropic. So the plane models, yes, indeed, it only has rotational symmetry in the plane, but no, there's no three-dimensional symmetry as far as I can tell. You can also see that from the dispersion relation of the photons. They're just very anisotropic. And the wire models are similar. They have the rotation symmetry. Well, they don't even have a rotation symmetry in the plane. I mean, the general models I wrote down. So I don't actually have, in general, I don't have any rotation symmetry in this system. I only have translation symmetry.